MS Ramaiah University of Applied Sciences.
Hi students, let us discuss heat treatment process of steel. Aim: to prepare the specimen for metallographic examination of different engineering materials. Introduction: the heat treatment includes heating and cooling operations to material in order to modify its metallurgical structure and alter its physical, mechanical and chemical properties. Heating the material to specific temperature, holding at this temperature for a definite period and cooling to room temperature or below with a definite rate. Annealing, normalizing, hardening and tempering are the four widely used heat treatment processes that affect the structure and properties and are assigned to meet the specific requirements from the semi-fabricated and finished components. Steels, being the most widely used materials in major engineering fabrications, undergo various heat treatment cycles depending on the requirements. Objectives of heat treatment processes: to increase strength, hardness and wear resistance. Bulk hardening, surface hardening. To increase ductility and softness. Tempering, recrystallization, annealing. To increase toughness. Tempering, recrystallization, annealing. To obtain fine grain size. Recrystallization, annealing, full annealing, normalizing. To remove internal stresses induced by differential deformation by cold working, non-uniform cooling from high temperature during casting and welding. Stress relief annealing. To improve machinability. Full annealing and normalizing. To improve cutting properties of tool steels. Hardening and tempering. To improve surface properties. Surface hardening, corrosion resistance, stabilizing treatment and high temperature resistance, precipitation hardening, surface treatment. To improve electrical properties, recrystallization, tempering, edge hardening. To improve magnetic properties, hardening, phase transformation. Laboratory chamber furnace. Annealing process. Annealing is a heat treatment process in which material is exposed to an elevated temperature for an extended time period and then slowly cooled. Typically, annealing is carried out to relieve stresses, increase softness, ductility and toughness, to produce a specific microstructure. Different annealing heat treatments are possible. They are characterized by the changes that are induced, which often are microstructural and are responsible for the alteration of the mechanical properties. Annealing process consists of three stages: heating to the desired temperature, holding or soaking at that temperature, and cooling, usually to room temperature. Normalizing. Normalizing process is similar to annealing and is carried out to avoid excessive softness in the material. The material is heated above austenitic phase and then cooled in air. This gives relatively faster cooling and hence enhanced hardness and less ductility. In this process, austenite is decomposed in ferrite and carbide at relatively lower temperature and fine pearlite is produced. Normalizing is less expensive than annealing. In normalization, variation in properties of different sections of a part is achieved. The selection of heat treatment operations is strongly influenced by the carbon content in the steel. Hardening. Hardening is performed to impart strength and hardness to alloys by heating up to a certain temperature depending on the material and cooling it rapidly. Steel is heated up to austenitic region and held there until its carbon is dissolved and then cooled rapidly. The carbon does not get sufficient time to escape and get dissipated in a lattice structure. This helps in locking the dislocation movements when stresses are applied. Quenching is performed to cool hot metal rapidly by immersing it in brine, that is salt water, oil, molten salt, air or gas. Quenching sets up residual stresses in the workpiece and sometimes results in cracks. Residual stresses are removed by annealing process. Effect of quenching medium and geometry. Effect of quenching medium. Air, severity of quench low, hardness low. Medium oil, severity of quench moderate, hardness moderate. Medium water, severity of quench high, hardness high. Effect of geometry. When surface to volume ratio increases, cooling rate increases. Hardness increases. Position center, cooling rate low, hardness low. Position surface, cooling rate high, hardness high. Tempering. Martensite is very hard and brittle. Tempering is applied to hardened steel to reduce brittleness, increase ductility and toughness, and relieve stresses in martensite structure. In this process, the steel is heated to lower critical temperature, keeping it there for about 1 hour, and then cooled slowly at prescribed rate. This process increases ductility and toughness but also reduces hardness, strength and wear resistance marginally. Increase in tempering temperature lowers the hardness. Stages of tempering. Slow cooling, medium cooling, fast cooling.
Hi students, today let us learn the heat treatment processes on the materials. Heat treatment includes heating and cooling operations to material in order to modify its metallurgical structure and alter its physical, mechanical and chemical properties. There are 4 heat treatment processes: annealing, normalizing, hardening, tempering. These are the 4 widely used heat treatment processes which affect the structure and properties assigned to meet the specific requirements. Now let us see the temperature versus time during heating process. We keep the samples at room temperature in the furnace and then start heating. Heating has to be carried out, which has to be crossed at upper critical temperature, that is 727 degrees centigrade. So heating has to be done above this for the particular time, and then it has to be soaking. After soaking, then the important process is cooling. During cooling, we get the 4 important processes like annealing, normalizing, hardening and tempering. Let us know more information on heating, soaking and cooling. Heating, as I said earlier, heating in furnace to temperature above upper critical temperature, that is 727 degrees centigrade. Soaking has to be carried out for sufficient time to obtain homogeneous austenite on the material. Cooling at different rate of time on the material. So now I will be explaining little more details the annealing. Keep the sample in the furnace at room temperature, then it has to be started heating for the speculated time, depends upon the cross section and the volume, and then it has to be soaked, then the furnace has to be switched on and it has to be cooled in the furnace. You can see we get the annealing heat treatment process on the material, that furnace cooling. it takes the longer time duration. So after carrying out the annealing heat treatment process, some of the advantages we get is that to relieve the internal stresses from the material, restore ductility and toughness, enhanced machinability, to refine grain size and grain structure, improve mechanical and magnetic properties from the annealed process. Next we go for normalizing heat treatment process. Again, keep the sample in the furnace at room temperature, then it has to be heated above upper critical temperature. At this point it has to be soaked for sufficient time, then it has to be cooled by keeping it outside atmosphere, air cooling, where you can see N normalizing. From this normalizing heat treatment process, we can tell that this is similar to annealing, but in normalizing it is air cooled as opposed to furnace cooling. From this normalizing, uniform placed perlite in equal size grain throughout the material we are going to get, stronger and somewhat less ductile than annealing process, improved physical properties. These are the things that we are going to get from normalizing. Next we go for hardening. Again, keep the sample in the furnace at the room temperature, then start heating above upper critical temperature. At this point start soaking to get the homogeneous, and then immediately quench it. There you can see it took the less time. Immediately quench it either in the water which is treated, or in the oil, or in the brine solution. So quenching that, the sample is called as the hardening heat treatment process. Cooling may be done, as it's told, by forced air, oil, or the brine solution. Austenite will turn to martensite. The material will be very hard and brittle. And the last heat treatment process is tempering. Again, keep the sample in the furnace at room temperature, heating above upper critical temperature, then soaking, then cooling in either water, oil, forced air, or brine solution, that we call it as quenching. At this point, after quenching, thoroughly clean the sample and reheat it. Maybe above 200 degrees centigrade, but less than 700 degrees centigrade. Based on the requirement of the application, it has to be reheated. After reheating, again the soaking operation has to be carried out to obtain homogeneous, and then it has to be air cooled by keeping it in the atmosphere. Then we get the T, that is tempered sample. Tempering, untempered martensite, very hard and brittle, reheated to impart toughness in the material for certain applications. So these are the 4 heat treatment process: annealing, normalizing, hardening, and tempering. Let us see that this process, how it works out on the furnace. Hi students, welcome to see the heat treatment process on the medium carbon steel that we have selected. Here you can see I have taken medium carbon steel. This is used to test the tensile test, and this is as per ASTM E8, and this is having carbon percentage 0.5%. And I have got another sample where this is also medium carbon steel. The one end I will use it to see the microstructure, and the other end I will use this for to check the hardness. I have taken 4 sets, one set for annealing process, second set for normalizing process, third set for hardening process, fourth set for tempering process. This is the electric heating furnace, which can be heated up to 1000 degrees centigrade, As I have taken the medium carbon steel, which has got 0.5% carbon, so I have to cross the upper critical temperature above 727 degrees centigrade. So I have set the program to 950 degrees centigrade. To start with, I'll switch it on. Then this is the panel which helps me to set the program. So there you can see it has been set to 950 degrees centigrade, and the heating time is 45 minutes based on the cross section of the material. Then next, soaking time is 30 minutes, again based on the cross section of the material. And then we have to carry out the cooling process. Now I will start the program. Before setting the program, let us keep the samples inside. This is the electric heating furnace. These are refractory bricks made up of ceramic, which can withstand temperature up to 1800 degrees centigrade. Inside on either side you have got heating coils. This is the area or the platform where we are keeping the samples. I'll keep one by one sample. Care should be taken that samples should not touch the coils. After keeping the samples, then the furnace door has to be closed. As earlier all the data has been set, now I will switch on the program. Now you can see process value and the set value. Which will go parallelly and reach 950 degrees centigrade by the time 45 minutes, then soaking 30 minutes. After the time is there, then we have to take out the samples in order to carry out normalizing, hardening and tempering, whereas the furnace has to be switched off and the sample has to be kept inside for furnace cooling to get annealed process. After 1 hour 15 minutes, that means 45 minutes heating, 30 minutes soaking at temperature 950 degree centigrade, as you can see on the panel. Now the samples are ready for the cooling process. As I said earlier, annealing, normalizing, hardening and tempering process will be shown here. Now I will open the furnace door and take out the samples one by one to carry out the heat treatment process. As you can see that all the samples are heated at 950 degrees centigrade for 1 hour 15 minutes. First sample, I will take it out and I will carry out quenching process. Here you can see that water is there. Tensile sample. And quench it. Now I will take the second set sample for normalizing process. I will take the sample which we can carry out microstructure and hardness. I'll keep it on the tray where it is kept open for air cooling. Similarly, I'll take the tensile sample and keep it here open for open air cooling. Now I'll take the third set of sample to carry out tempering process. First the sample for hardness and microstructure. First I'll quench it in water. The tensile test sample. For tempering process, after it is quenched, the sample has to be thoroughly cleaned. Now I will take the help of oven to reheat the sample after cleaning. This is a heating oven which can be heated up to 400 degrees centigrade. I'll switch on the power. Now I'll open the door. I'll keep the cleaned samples after quenching where the oven is set to 250 degrees centigrade. So this heating will take place for half an hour, soaking for half an hour, total 1 hour. Then I will close the door. Tempering process. First we heated the sample in the heating furnace, and after that it was quenched in water, thoroughly cleaned and kept in the oven for reheating. And you can see on the panel it was reheated to 250 degrees centigrade for 1 hour. That includes half an hour heating, half an hour soaking. Now it's the time to take out the sample from the oven. I'll switch off the heating. Now you can see the samples are reheated to 250 degrees centigrade for 1 hour. I'll take out the sample for microstructure and hardness and keep it for air cooling. Now I'll take the tensile test sample. Keep it on the tray for air cooling. Now the fourth set of sample for annealing process, as you can see here, which is inside. One sample for hardness and microstructure, another sample for tensile test. I'll close the door and switch off the heating unit, program and the mains, and this is the furnace cooling. For the annealing heat treatment process, we had kept the sample inside the furnace for furnace cooling. So after 48 hours, the sample has attained room temperature. Now we have to take out from the furnace. can see that it has attained the room temperature. And this sample for hardness and microstructure, which has also attained room temperature. Hi students, welcome back. After doing the heat treatment process on the steel like annealing, normalizing, quenching and hardening, let us do the tensile test on all the samples. For that we have got a universal testing machine. On this tensile test is carried out, and we have got a computerized setup where the data is analyzed. These are the 4 tensile test samples after heat treatment as per ASTM standard E8. Annealed sample, normalized sample, quenched sample, tempered sample. Now let us carry out tensile test on all the 4 samples. Now we will take the annealed sample for tensile testing. Let us fix the sample first in the upper arm. Clamp the lower portion of the tensile test specimen to the middle arm. We have got a software which helps us to capture the data and then analyze it. Test type, tensile, load versus displacement, specimen, round, test data, annealed sample, initial diameter 12.5, gauge length 62.5 as per ASTM standard E8. Units kilonewton per mm square. Online scale, this is the range where we can keep the x-axis and the y-axis. X-axis for deformation, y-axis for load. And then now it is ready for the start test. Switch on the hydraulic pump and make the scale online and set 0 load and 0 displacement and then say yes. Here the loading is given, a constant load is applied. You can see load versus displacement graph is generated. Now you can see cup and cone like necking. After the sample is tested, if you see the fracture area, you can see cup and cone arrangement. The material has become ductile and more soft. That is the process of annealing. Similarly, test has been carried out on normalized sample. You can see the fracture area. Next you have got the quenched sample. and this is the fracture area. The material has become hard and brittle. Finally, the tempered sample. The material has attained toughness. This completes the experiment. Thank you.
At MSR UAS, we spark your imagination unlike any other.